Pleasure to welcome all of you on behalf of ISI, the International Space Science Institute in Bern, Switzerland, to today's talk in ISI's Game Changer series. I'm Joachim Mamsgans, Director for Astrophysics and Cosmology at ISI and your host today. ISI has served the space science community for a quarter of a century by offering various tools for scientists to meet in Bern and jointly do science related to space missions. In July last year, we introduced the ISI Online Game Changer seminar series as one of the few new tools because physical meetings in Bern were not possible. After a short break in April, we restarted 2 weeks ago, and we will have a talk every Thursday until the summer break. In case you missed any of our previous talks, they were recorded and can be viewed on the ISI website. Before I introduce today's speaker, let me announce next week's seminar. Philippe Lognonnet will talk about terrestrial planetary seismology. We are very happy to have Adam Riess as today's speaker. Adam studied at MIT and received his PhD from Harvard in 1996. He was a Miller Fellow at UC Berkeley before he joined the STScI, the Space Telescope Science Institute in Baltimore. In 2006, he became a full professor, and in 2016, Bloomberg Distinguished Professor at Johns Hopkins there. Since 1998, Adam Riess has led the High-z Supernova Search Project jointly with Brian Schmidt. Through discovering and monitoring supernovae of type 1a, they provided evidence that the universe expansion rate is accelerating. Adam has received numerous prizes and awards for his research. Let me just mention one. Jointly with Brian Schmidt and Saul Perlmutter, he won the Nobel Prize in Physics in 2011 for the discovery that the expansion of the universe is accelerating. Without further ado, I'll hand over. Adam, the stage is yours. We're all very excited to hear your talk on the Hubble constant controversy.
Thank you. Well, it's a pleasure to sort of virtually be here. I'm going to tell you about recent progress in measuring the Hubble constant, the expansion rate of the universe, using a wide range of techniques, and how we continue to see evidence of the universe expanding faster than expected. This is work mostly on behalf of the SHOES team, and if you want to read about some of the details of this work that I'm going to describe, I could recommend a number of reviews, but also this paper in the lower left here. So let me start back at the beginning a little bit. One of the only ways we really have of learning about the composition, the age, and the fate of the universe is by watching it expand around us, and of course, measuring that. Given that the universe is homogeneous and isotropic on large scales, and assuming that it obeys general relativity, we can derive an equation of motion for the universe, how the universe, or the scale factor, the size of the grid that you see there, A, how that changes with time as a result of the physics, as a result of the forces, the dynamics, the gravity in particular in the universe. Now, we cannot directly measure A, nor can we directly measure time. However, we can observe proxies for both of these. So we can observe redshifts, of course, that's closely related to A, and we can attempt to measure distances to objects in the universe. And through knowledge of the speed of light, of course, that allows us to determine how far back in time or how far away we're looking. Now, the equation of motion for the universe described in this way is known as the Friedmann equation. It's in the lower right. And the observer's quest then is to measure the left-hand side, how A changes with time. This is the kinematics of the expansion. And in doing that, to learn about the right-hand side of the equation. That's the interesting composition of the universe and the physics of that composition. And if we can extend our measurements out in distance or in time, we can see how A has changed with time. That is, we can measure the differential part, and that tells us more about the right-hand side of the equation. So it used to be that this job was relatively simple when we thought the universe was just matter dominated. Then we really only had to measure the first two derivatives of A to learn most of what we needed to know. The first derivative of A, of course, is just the expansion rate, and defined at time now, where redshift 0 is known as the Hubble constant that sets the size scale and age scale. And up till a couple of decades ago, this was hotly debated over a factor of 2 in uncertainty, either that we lived in a big old universe that was slowly expanding, that is H0 of 50, or we lived in a small, sprightly, expanding universe that was relatively young, that is Hubble constant of 100. The other of these two quantities, of course, is the second derivative of A, how that expansion rate changes with time. And again, a couple of decades ago, the expectation was that it was decelerating because of the gravity of attractive matter in the universe, that by measuring the deceleration, you would determine the mass density of the universe and the ultimate fate, as well as the geometry of the universe, and further, even the viability of inflation, the theory of what happened shortly after the Big Bang, because that made predictions about the mass density of the universe. Now, the 1990s was really a special time, I would say, in this quest, because it became possible for the first time to really precisely measure the long-range distances, particularly with what astronomers call standard candles, to measure those distances and therefore these quantities. So just a brief couple of words about standard candles. Of course, if we understand the luminosity or relative luminosity of the object we're looking at, then its brightness tells us the distance. And so I'm going to talk about two kinds of standard candles primarily for this talk. The type 1a supernovae, which are exploding white dwarf stars. These are stars that approach the Chandrasekhar limit as white dwarfs. The details of how they do this are still quite debated and I would say unclear, but we believe it involves being in a binary system, another star and some mass transfer. And when it reaches the Chandrasekhar limit, gives us a fairly uniform explosion of a billion or a few billion solar luminosities. The second kind of standard candle I'm going to discuss are supergiant stars called Cepheid variables that pulsate because they're constantly overshooting an equilibrium called hydrostatic equilibrium. And these are 100,000 solar luminosities, and they exhibit a very strong coupling between the period of the oscillation and the mass of the star or its luminosity. And in practice, these are kind of idealized cases. In reality, we make small corrections to actually standardize these kinds of objects based on additional individual information, such as the shape of the rise and fall of the light curve, or the color of the object, which tells us whether there is any intervening dust in the universe that tends to redden the light as well as dim it. Okay, so I'm going to fast forward now to essentially the early 2000s when, as you heard earlier, the two teams of astronomers, the High-z team, and I see Bruno Leimegood here on the call from there, maybe others as well, I didn't check recently, and the Supernova Cosmology Project discovered, to their shock, that neither of those stories about the deceleration of the universe was right. In fact, the universe looks more like on the right. That Q naught, the deceleration is negative, that is, the universe is accelerating. And by the early 2000s, it was found that the Hubble constant was sort of in the low 70s, about in between that range, but with a fairly wide uncertainty. And this is more or less how things stood, harmoniously, but with big questions on our mind, like, why is it that the universe is accelerating? What does that mean, or what is the underlying physics? And so looking at this more generally, as physicists do, three possibilities have more or less emerged. One is that there is a background energy in the universe, what we might call vacuum energy, or what Einstein might have called the cosmological constant, and is given the name lambda, so that our new cosmological model this way would be called LambdaCDM for lambda and cold dark matter. And this is the idea really that comes to us from quantum mechanics, that there should be a background energy in empty space married to general relativity, which tells us such a background energy would produce a repulsive gravity. Unfortunately, there's a terrible quantitative mismatch between the motivation of this idea and general relativity, about 120 orders of magnitude. Option number two is that this is a dynamical dark energy. That is, there is a background energy, but it's produced not intrinsically to space, but is the potential energy of a field in space that may be changing over time. We see existence proofs, I would say, for both of these possibilities, but we don't know if either of them or one of them is ultimately the right story. A third possibility, of course, is a modification to general relativity. That is, that gravity, as described in general relativity, does not operate as expected over very long ranges in the universe. And there are many tests going on for these. And so one might wonder, how do you proceed in a situation like this, where you have these different possibilities? And the answer, the pragmatic answer, is option one, while it's the simplest, is also the simplest to calculate. It's the simplest because it makes a very specific prediction, whereas number 2 and 3 are sort of a range of possibilities. And so the way we proceed logically is more or less to assume number 1 and do calculations and make predictions and then look for departures or differences. So now I'm going to move into the contemporary part of this talk for background, which is what I think of as the sort of grandest end-to-end test for option 1 of vanilla LambdaCDM. And that is, we will assume for the moment that vanilla LambdaCDM, and when I say vanilla, I mean the simplest form of LambdaCDM, is true, and then make predictions. And when I say the simplest, I mean that, for example, the universe is 95% now dark matter and dark energy, and we don't understand the microphysics of those. So we make the simplest assumptions that dark matter is a particle without interactions, that it's stable, that dark energy is, as I said, option number 1. And then we take the model as it would have looked early in the history of the universe, before recombination, shortly after the Big Bang, when it would have been dominated by atoms and photons and neutrinos. And we use that model to predict the physical size of fluctuations in the plasma of the early universe. Foremost of those are the sound horizon, the distance a fluctuation can travel from the time of the Big Bang till the universe becomes transparent, or the baryon density. And then we compare those predictions to observations from the early universe of the cosmic microwave background particularly, but also could be the baryon density. And in that comparison step, we are essentially calibrating the 6 free parameters of this new standard model. We then use that model and as it would have changed and evolved over the next 13 some billion years, and it eventually would evolve to look like this, to predict the expansion history of the universe. We get some checks along the way from distant supernovae and other features in the large-scale structure of the universe. And finally, that path predicts how fast the universe ought to be expanding today. And the most precise cosmic microwave background data comes from the Planck satellite, the European satellite. And that prediction then is that the Hubble constant today should be 67.4 plus or minus 0.5, a very precise prediction, but admittedly based on, as I said, the simplest model with some fairly vanilla predictions of the dark components of the universe. Therefore, a very powerful end-to-end test of this whole story is to measure the actual expansion rate, what we actually see today, the Hubble constant, and compare it to this prediction. And so about 15 years ago, my colleagues and I set out to undertake a project with the Hubble Space Telescope to do this, to measure the Hubble constant locally to very high precision, to reach percent level precision, using what I would say are the sort of gold standard tools of making such measurements. And that was to build a strong and simple distance ladder using geometry to calibrate the Cepheids that I talked about, and use the Cepheids to calibrate the type 1a supernovae out into the expansion of the universe. And so we saw a number of ways to reduce systematic uncertainties over past measurements. We chose to make our measurements in the near infrared to reduce the impacts of dust, which has always plagued astronomers. Also, we wanted to do a sophisticated simultaneous analysis to really keep track of and propagate all the statistical and systematic errors, as well as, crucially, the covariance between data and model. This was not a key project. This followed the key project. So this was a second generation project based on 17 individual proposals. So the Hubble Space Telescope competed. Now, totaling about 1,000 orbits of time. Okay, so let me just walk you through the measurements that I'm talking about. And I first need to describe what a distance ladder is and how it works in this case. A distance ladder is the simplest and empirical thing you can do to measure distances, but it must be consistent. It must be consistently measured. And so let me tell you what I mean by that. The first step we call the anchor step, where we use geometry, a number of different ways of doing this to reach Cepheid variables, which are kiloparsecs to megaparsecs away. Then we identify a number of galaxies at an intermediate distance range, 10 to 40 megaparsecs, that hosted type 1a supernovae recently, where we can then go and observe Cepheid variables in those galaxies with the Hubble Space Telescope. And then finally, the type 1a supernovae are observed well out into the expanding universe, where their redshifts are used to calibrate the Hubble constant. So as I said, this is relatively straightforward. There's no astrophysical modeling. This is completely empirical. There's no use really of general relativity or the cosmological model in this. However, it's critical that the measurements made across rungs in this ladder are consistent. So we have put a great deal of effort to produce homogeneous measurements, really differential measurements between Cepheids observed with the same telescope and type 1a supernovae, and I'll talk more about that later. So let me just mention first the first step, geometry. Of course, if you sort of know basic geometry, then you know about parallax, the ability to measure the distance, in this case to a star, by observing the change in position of the star as the Earth goes around the sun. This is straightforward. However, it's just challenging because stars are very far away. And so the parallax angle becomes very small. For typical Cepheid variables, which are kiloparsecs away, you're looking to tell that a star has moved back and forth by 1/100th of a pixel on the Hubble Space Telescope. That is very challenging. And really, the problem comes down to how well you can centroid a star, figure out where it actually is relative to other stars in a pixelated image. We came up with a significant improvement in this process a few years ago by figuring out to spatially scan the telescope during the measurements so that we could compare the separations between stars on a single frame thousands of times to essentially beat down errors in these measurements. We literally allow the sky to scan by and turn these images into really lines of charge. And then we measure the separation. Here's a little patch of one of these images. And then we extract these scan line by scan line. And after we subtract any two scan lines, this removes the jitter of the telescope and allows us to really reduce uncertainties down to 20 to 40 micro arcseconds, about 1,000th of a pixel on the Hubble Space Telescope. And so using this approach, which I call approach one, using the Hubble Space Telescope to spatially scan and also to measure the brightnesses of the Cepheids. We did this for about 8 long period Milky Way Cepheids over the last few years. What you see here is for each Cepheid, the back and forth motion every 6 months is due to parallax. So the amplitude of this tells you the parallax, and the inverse tells you the distance. So a few years ago, we did this to about 3% uncertainty. What I call approach 2 has gotten much, much better. And this is using the Gaia European Space Agency satellite to measure parallax for many Milky Way Cepheids. This is a mission that was designed to measure parallaxes to very high precision. And now in data release 3 has reached a precision that really just now surpasses what we could do with Hubble, but for many more stars. And so using 75 Milky Way Cepheids, not just 8, and using the Hubble Space Telescope still to measure the brightnesses of those Cepheids so that they're on the same scale as the distant Cepheids we're going to observe, we've been able to reach now 1% precision. I'm going to show you more in detail how powerful this data really is. And so we can now look at this, what I described to you before as this relationship between the period and the luminosity for Cepheids. That gives us a very precise calibration. You just measure the period of any given Cepheid, and then you've determined its luminosity. And these most recent 2 approaches have given distinct advantages over the past, where we can now observe the brightness of the Cepheid with Hubble. When Gaia reaches its final expected precision, this should calibrate the Hubble constant to about 0.4%. So this really has been a great step forward. Okay, parallax is not the only way to geometrically calibrate the luminosity of Cepheids. There are at least two other ways that we use. Using a special kind of binary system called a detached eclipsing binary, we can geometrically measure the distance to the Large Magellanic Cloud, which has hosts many Cepheid variables. This was done recently by Gregor Petrinsky and his group. And third is to observe water masers in Keplerian motion around a supermassive black hole. And these water masers have been tracked now for 20 years in the radio to measure their proper motion and their line of sight acceleration, which also gives a geometric distance to Cepheid variables in that galaxy. And so each of these methods now calibrates our basic distance ladder separately to 1%, 1.3%, or 1.5%. And of course, most importantly, allows us to cross-check these different methods. Okay. Moving on to rung number 2, I told you this is where there are galaxies at intermediate distances that once hosted a type 1a supernova, and we go back with the Hubble Space Telescope and observe Cepheid variables in those galaxies. Now, this is really the rate limiting step for measuring the Hubble constant. Each type 1a supernova is good to about 6%. So 6% over square root of n, the number of such supernovae really limits the precision of the Hubble constant. Up till about 2016, we had been able to measure about 19 of these type 1a supernovae with Cepheids, and we're just in the process now of doubling that sample, maybe even a little more than doubling that sample. And in the next few months, we hope to release those results. Here are the period luminosity relations for the Cepheid variables, now not in the Milky Way, but in each of these individual supernova host galaxies. We observe these in 3 bands, visual, infrared, and the near-infrared, the H band, as well as in the 3 anchors. As I said, one of the ways we've been able to reduce systematic errors over past generation measurements is we observe the Cepheid variables, not just in the supernova host galaxies where only Hubble can do this, but also in these nearby anchor galaxies where they're very bright, but we want Hubble to do this so that we can measure a purely differential measurement. We also take great effort to measure Cepheids over the same range of chemical abundance and period. Here are the composite light curves of the Cepheid variables in each of these galaxies and in, for example, NGC 4258. Another big improvement we've made is by making the measurements in the near infrared, we reduce the impact of differential dust. So Cepheids are better distance indicators. And so this is nicely seen in the period luminosity relations of the Cepheids in the Large Magellanic Cloud, our nearest neighbor. As you go from the optical or short wavelength to longer wavelengths, you can see the tightening of this relation. That's the reduction of differential dust. And of course, we then use colors to still further remove any of the effects of dust. The third rung is really well developed because of all the work done over the last decades to measure the acceleration, of the universe, and that is to measure the Hubble expansion as seen by supernovae. And so we measure what is known as the intercept of the Hubble diagram, the characteristic brightness as a function of redshift, taking account for small changes in the expansion rate between redshift 0 and, let's say, redshift 0.1, which is very small in cosmology terms, but it's not 0. So we want to account for that as well. And then finally, we put all 3 of these steps together, and this is more or less what the data looks like, one continuous distance ladder, where you start out with geometry calibrating Cepheid variables calibrating type 1a supernovae, and type 1a supernovae calibrating redshift and therefore the Hubble constant. And our most recent results using the Gaia data release 3 to really boost this precision is 73.2 plus or minus 1.3, so a total uncertainty of 1.8%, but noticeably larger than the value that was predicted earlier in this talk. In fact, it's about 4.2 sigma from the cosmic microwave background plus the cosmological model used to predict the expansion rate today. So what's going on? Is it a problem in the first rung? Well, this is where we have the power of independent ways of measuring the geometry to the geometric distance to Cepheids. And so I showed the three primary ways: the Gaia parallaxes, the water masers in 4258, or the LMC detached eclipsing binaries. And they give very consistent results, all consistently inconsistent with what we see from the cosmic microwave background plus LambdaCDM. And then there are a number of additional checks on these, lower precision but independent measurements, for example, the spatial scan measurements that I talked about. And these all give a little noisier but still very consistent results, indicating this is we really cannot find any indication of a problem in the anchor step. So then I just want to show you in a little more detail how much Gaia has improved just in the last data release. This was the status of, this is the predicted parallaxes based on the value of the Hubble constant. That is, you could turn the distance ladder in reverse, start out with the value of the Hubble constant and state what the parallaxes of the Cepheid should be. And then this is what Gaia actually measures them to be. And these are for about 50 Cepheids in the Milky Way where we had Hubble Space Telescope observations. And then so you could see here that the data favored a higher Hubble constant, but certainly the data wasn't that impressive. Here we are now, 2 years later, with Gaia data release 3. More Cepheids have been observed, particularly nearer ones, with both Gaia and the Hubble Space Telescope. And the data has sharpened up quite a bit so that this is now a very strong anchor. I'll jump between these for a moment. If you look particularly at the distant end where the sample is not changed between these two updates, all the improvement, the tightening you see, is coming from Gaia 3. Okay, so how big a difference are we talking about at this point? Well, to astronomers, right, in our units, it's 0.2 of a magnitude in any one of these steps. That's quite large. We looked at 23 variants of the analysis, changing the way dust reddens luminosity, changing the way you remove a small number of outliers of Cepheids, changing the period range, changing the period luminosity relationship from a single slope to a broken slope, changing the way you fit supernova light curves, changing what kind of host galaxies of supernovae you allow, because if you allow only spirals or locally star-forming ones, you better match the nearby ones that are Cepheid hosts. But none of these things makes a significant difference. However, it does increase uncertainty, which we add into our systematic error at the end. Additional questions I am frequently asked that I'll just take the opportunity to anticipate people thinking of. Could it be that we live in a giant void so that the universe is expanding faster around us? This would have to be about 9% in the Hubble constant, which would be an enormous density contrast, almost a factor of 50%. And no, we don't see that in large scale structure theory when we do n-body simulations, or when we look at the supernova Hubble diagram itself. It extends out to redshift 1. And so if we did live in a bubble, you would see a kink in the Hubble diagram. We can place limits from both of these independently to about 0.6% in the Hubble constant. Is the Hubble Space Telescope's Wide Field Camera 3 calibrated well enough to make this measurement? And the answer is yes. It's been calibrated to about 0.3% in the Hubble constant across the dynamic range that it has to observe. Could the crowding of Cepheids compromise their accuracy? We have many now independent tests that the accuracy has not been compromised. The most recent one comes from the amplitude data from Cepheid variables. The fact that if you had crowding you didn't recognize, it would suppress or compress the amplitudes of the variable Cepheids, and we see no evidence of that. It places very strong limits. Could there be a difference in the type 1a supernovae at the two ends of the distance ladder? I remind you, we're only talking about relatively low redshift supernovae, redshifts of 0.05 to 0.1 versus 0.01. So these are very small look back times. However, we look for correlations in the Hubble residuals with other properties of galaxies, and these are generally not significant and at most would change the Hubble constant by about 0.3%. Is it just us seeing this? And the answer is no. The community has more or less been seeing this for about 20 years, I would say, using Cepheids and type 1a supernovae. Whichever team does it, a different team than us, the Key Project, different ways of measuring photometry, different groups of people, Planck people, reanalyzing our data, using different supernovae, using infrared observations of supernovae, doing different sophisticated statistical analyses. It's even a graduate student problem set in the University of Toronto. Always sees in this range of about 71 to 76. Most recently, a group, the Araucaria group in Europe and South America, went back to the Hubble archive and grabbed the original pixels from our data and started literally from scratch using different methods and never spoke to us until they finished and published their paper and got the same answer to about 1% agreement. So, you know, this seems to be what we see on the sky. Now, of course, there are many other ways of or other data sets for measuring both the local expansion rate or from the early universe measuring and predicting the expansion rate. And there's been a lot of other work on this. And we had a review of this about 2 years ago, and there's been ongoing work since then, but different methods using Cepheids and type 1a supernovae by different authors, TRGB and type 1a supernovae, masers and type 1a supernovae, Tully-Fisher, surface brightness fluctuations, lensing. These are all the more precise claimed better than 4% measures in this review by D. Valentino that came out about a month ago. And these are the early universe measurements. So using not Planck, but WMAP or ACT or SPT, or not using the CMB at all, but using BBN, Big Bang nucleosynthesis. It seems like when you start from early universe physics or LambdaCDM in the early universe, you get consistently lower results than you get from these. And you can remove any one method and you still are going to be somewhere between 4 and 6 sigma. And you could consult this review or this review, and there's been at least a few others recently. I want to mention Gaia is not just helping calibrate Cepheids, but as well as other stellar populations that are used to calibrate type 1a supernovae. For example, tip of the red giant branch, which is the most luminous a red giant star becomes. And this has been challenging to calibrate because there's no one star that is the tip of the red giant branch. It's the peak brightness of a population of stars. So you can't measure the parallax to individual stars very effectively. However, you can measure the parallax to the nearest globular cluster, Omega Centauri, now with Gaia Data Release 3. This is, I would say, the best direct calibration of TRGB in the Milky Way because Omega Centauri is big enough to have a fully populated red giant branch. And this has now been done. I did this work with John Soltis and Stefano Casertano, measuring 67,000 stars in Gaia, measuring their color magnitude diagram. And here's the tip of the red giant branch. And you can identify it. You can measure the parallax of Omega Centauri from Gaia DR3, and it comes in about 5.25 kiloparsecs. And that is consistent across the full magnitude range of the color magnitude diagram. And if you use the pre-existing tip of the red giant branch measurement in this galaxy, you get a calibration that really helps improve the calibration of tip of the red giant branch. You get about 72 plus or minus 2, very consistent with what we see with some of the other methods. And there are now 4 groups that have done this independently using Gaia to measure Omega Centauri's parallax, and they all agree quite well. Our uncertainty is about in the middle of the range of these. Now, interestingly, it's not just the Hubble constant where we're seeing this tension between early and late. There's some indication of tension in another aspect of the cosmological model, that is the prediction of how clumpy the universe ought to be, a parameter known as sigma 8, the fluctuations in cells of about 8 megaparsecs on a side. And here 0.8 is about the dividing line. Planck predicts the universe should be clumpier, and yet local measurements from weak lensing or peculiar velocities independently get about 3 sigma smoother for the universe. And so the sort of combination makes it look like the universe is both faster and smoother than you would have expected. This is not as significant as the Hubble tension, but it's getting there, and it's worth keeping your eye on, and it's worth thinking about in the context of possible solutions. So let me be clear, I don't know what's going on. I don't have an answer or even a favored solution, but I will say that, it's tempting to think about new physics, since it does seem to be an early versus late discrepancy, or basically a discrepancy that shows up when using the model to connect early and late. And many other people have thought about this. And again, I could direct you to a number of reviews here, this one by D. Valentino or this one by Knox and Malaya, who have looked at all kinds of ideas that have been published. So one possibility is an episode of early dark energy in the universe shortly before recombination, changing the properties of neutrinos, adding a neutrino, decaying dark matter. All of these will have some effect on the predicted value of the Hubble constant or of the clumpiness of matter. Some make things worse, like decaying dark matter, or will make the overall fit worse, or sorry, I don't mean to say will make it worse, are worse options because of how they match the data. So decaying dark matter, equation of state less than -1, swampland. Things that look a little more promising would be strong neutrino interactions, early dark energy, changing the electron mass, making recombination happen earlier, primordial magnetic fields. Basically, the best ideas do the following. They, in some way, inject energy in the early universe before recombination, causing the universe to expand faster earlier, making the universe become transparent earlier, which shrinks the sound horizon, which essentially changes the calibration of the cosmic microwave background and its predicted value of, for example, the Hubble constant. I still suspect the best idea is the one that we haven't thought of yet. And none of these ideas is particularly more compelling than other ones, or overwhelmingly compelling, which is why there's still so much, I would say, uncertainty about this. So what we need at this point, I think, are very specific hypotheses. What I would really like to get across, if only one thing, is that the data has gotten very, very good. And so therefore, it presents a very formidable challenge. It presents a formidable challenge both to a statement that it's new physics, because there's such good constraints on the expansion rate of the universe and from the cosmic microwave background that you can't just wave your arms and invoke new physics. We need specific story of what that looks like to test it against the data, because a lot of it won't make it. Also, likewise, when people say it's systematics, again, the data has gotten sort of too good to wave your arms. There are too many measures. There's too many independent cross-checked measures, independent rungs, duplication, or just plain, having to violate the Copernican principle of living in a very, very, very special place to sort of wave your arms in this way. Again, we need a specific explanation of what is going wrong, or in which kind of object or measurement. So I would say, in my humble opinion at this point, the data is just too good for non-specific claims or even nitpicking individual results. It's clear there's some kind of signal, and it really at this point demands some kind of testable and specific explanation. However, having said that, we're not painted in such a tight corner because we have so much more information coming, both new data from new facilities, LIGO, DESI, Roman, Rubin, Euclid, JWST, Simons, S4. There's some additional clues which seem to be, on the edge of telling us something maybe related, maybe not. But the most important thing I think to keep in mind is LambdaCDM, vanilla LambdaCDM, is still a pretty big playground. It's 95% without detailed explanation of physics, and lurking in the background always is the lack of a quantum gravity theory, which we know, at some level must sort of supplant or help us understand quantum and general relativity's incompatibility. So it's therefore worth keeping an open mind. We are in the process of more than doubling the sample now of Cepheid supernova calibrators, which is the rate limiting step for our measurement. And so we hope in the next few months to be releasing our final results from this. The uncertainties have steadily come down over the last 15 years. by a wide range of work by many people, just sort of documenting this here. The value has not changed very much. And we hope in this next iteration to finally get down to about 1.2%. That and the other missions that I talked about, hopefully giving us new clues. I think, as they say, watch this space or stay tuned. So my final thoughts before I end is I think at this point, the discrepancy it's around 5 sigma. Could be as low as 4, as high as 6. It really depends on which kinds of measurements you want to combine, but it is hard to avoid. Another way of saying this, I think at this point, is there's no precise late universe measurement that's coming in lower than the early universe measurements. That is in itself quite interesting. I think it's robust. It would really require multiple, I would say, catastrophic failures to get out of this particular problem. And therefore, I think it's very interesting. Unless you have a very strong Bayesian prior on vanilla LambdaCDM, or you're willing to throw away a lot of data, I think this is something serious to contend with. And I think we need to look for explanations that make very specific or testable predictions in order to be able to make some progress on this. So hopefully I gave you sufficient background in this, and happy to take any questions that you have.
Well, thank you very much indeed, Adam. And let me give you a big hand. You have to multiply this by a factor 300. We had 300 participants. Wonderful talk, very nice illustrations, figures, really. And we Europeans are particularly happy that you praised Gaia so much, because yeah, we all are happy that Gaia was working so well.
Yes, let me also, if I didn't make it clear, praise Planck as well. I mean, they're both incredible missions. We just see this discrepancy, but that could be interesting. It's nobody's fault.
Indeed. So to the audience, you can either type your question to the chat or raise your hand, and we will have about 18 minutes for Adam, because he has to leave sharp at 6 o'clock European time. So let me open the chat. There are already a couple of questions there. Let me try to do it chronologically. Henny Lamas asks, what about the metallicity, question mark? We wanna...
Right. So I'm not totally sure where she's referring to metallicity. I'm going to assume that she's talking about Cepheids and metallicity, because that's probably been, the most well-known place metallicity shows up. So we benefited from the recognition at least 2 decades ago that there was a dependence for Cepheid luminosity on metallicity. And so we've been measuring the metallicities of all of the host galaxies in which we observe Cepheids, and we calibrate out a metallicity relation. You could call it a nuisance parameter. And we get very similar metallicity results as people in the literature have been getting. It has a very minimal effect on the Hubble constant, and that's because most of our host galaxies are big spiral galaxies. They're metal rich. And most of our calibrators, like the Milky Way and NGC 4258, are also big spiral galaxies, metal rich. So it has no real differential effect. The one exception would be the Large Magellanic Cloud, which is a little more metal poor. And so sometimes an additional test is to look at the Hubble constant we get from the Large Magellanic Cloud only versus the 2 metal rich galaxies. But they're very similar. And as I said, we calibrate it out, and it has a very small effect on the Hubble constant.
William Wall asks, how about the gravitational constant G varying slightly?
Yeah, there have been papers that have suggested that, and they're serious papers, and it is, it's a possibility. It's complicated to figure out what it does, because when people think about big G, they usually jump right to the effect on the expansion rate of the universe, like the Friedmann equation. But, big G also shows up in the Chandrasekhar mass for type 1a supernovae. And so, it's not, I've never seen anybody address both aspects of that. In general, it's difficult to work an evolution of a parameter into this problem, just because we're not talking about very much look back time. We're talking about a few 100 million years. So you need a very fast evolution. And, then when we go to the high redshift universe, things ought to really be crazy, and they don't seem to be. But, again, a detailed story of what that would look like can be tested against the data.
Thanks. Henny Lamas again, is it possible that the dust ISM property is changing with distance?
So again, there's a range of sort of thoughts on this. The first is we're making our measurements in the near infrared in 1.6 microns, where the effective dust is very low. And then on top of that, we're accounting for reddening. And there was a nice paper by Knox and Folan, or Folan and Knox, that analyzed the reddening or dust properties at each of the host galaxies in our distance ladder, and played with uncertainty there, and found that they could not change the Hubble constant by looking at variations in what's called the reddening ratios. So that does not really look like it's in the cards.
Hugh Hudson asks, is the Hubble constant settling towards the value that Sandage preferred decades ago?
Sandage actually, right. Sandage initially, I think, preferred 75. I think that's my lore memory, is those were his initial results. So you could almost say yes, but then he became quite convinced that the Hubble constant was in the 50s. But part of that was from measurements, but a lot of that was actually, he was under the, I would say, wrong impression that the mass density of the universe was 1, that omega matter was 1. And if omega matter is 1, then the age of the universe is really 1 over the Hubble constant times 2/3. That 2/3 factor is the painful part. It makes the universe really quite young. And so if the Hubble constant wasn't, at least in the 50s, then the universe could end up being younger than the oldest stars in it. So I would say the real resolution of that problem was the discovery that omega matter is not 1, that the universe is accelerating. That 2/3 factor became a 1, in which case, the Hubble constant really can be in the 60s or 70s. And so, that was very late in Sandage's life, and I did not speak to him. So I don't know how he felt about that, what he ultimately thought the Hubble constant was. He, as I said, he did really important work, and, had worked at, without full information, I would say.
Yeah, and if I may add, Sandage worked with Gustav Tammann, who, of course,
Yes.
was a Swiss scientist and also
Yes.
was very important for the EC in Bern. So there is a tradition of,
Yes. No, I understand. And they did, they did a lot of trailblazing work in these areas. To me, the big limitations they had is they didn't have a few things that we have now, tools. They didn't have the Hubble Space Telescope with its updated cameras, which has been just absolutely critical to this work. They mostly didn't have the benefit of the Hubble diagram of type 1a supernovae observed with CCDs, and they didn't know the other cosmological parameters very well. And so, these were real limitations.
Martin Topinka writes, thank you for the great talk. From what you're saying, is the possibility of inhomogeneity and isotropy of the universe ruled out?
I wouldn't say it's ruled out. It can certainly have impact. I guess what I was saying was that attributing it to one giant inhomogeneity, which would be us living in the center of an enormous void, does seem to be ruled out. First of all, there's the huge coincidence problem. If you are off center of such a giant void, you create a giant flow with us moving towards one side of it, and that produces a giant dipole motion, which should show up then as a red and blue shift, one direction and the other, in the cosmic microwave background. And that is not seen. A small dipole is seen, but that's just, a normal sized motion of a galaxy. We don't see any extraordinary motion. So you'd have to be in the dead center of such an enormous void. And as I said, when you do large scale structure simulations, n-body simulations, throwing the observer in random locations, the void that you would need to solve this problem would be like a 10 or 15 sigma sized void. So, that would become a way bigger problem than this one.
Ambrosio Colombo writes, thank you for the wonderful presentation. My question is, given the compatibility of many methods in the late universe, do you expect that the measurements of standard sirens in the next years are going to be consistent with the supernova 1A values?
Well, I can make an empirical prediction that the measurements of standard sirens empirically, I expect would give something in the 70s, because, generally that's what we see from other measures in the late universe. It's a very important measurement to make, and I'm very interested to see what they get. but I mean, so we'll have to see. I think LIGO should come back online maybe next year. One of the challenges of LIGO, 5 years ago, many of us thought, oh, LIGO is really going to make a big impact in this field. But it turns out that the rate of the kinds of objects that they can measure best for this problem, standard sirens, but kilinovae in particular, are probably pretty rare, probably rarer than we thought. And so, the first one was found in 2017, and then there were really no others found for a few years, which tells us that they're pretty rare. So I don't know the time scale on which LIGO will make a contribution. I think they will make a contribution. It might even be a very important one. I just, I don't know whether we're talking a couple of years or a decade.
Jose Diego asks, did not DES find a lower value for H0?
So what you have to be very careful with when you're comparing values of H0 is how they're measuring H0, because this is a difference between using early universe physics to calibrate or using local measurements. And so in the case of DES, they were using what's called an inverse distance ladder. They were starting in the early universe. They were starting with either Big Bang nucleosynthesis or the cosmic microwave background, using that to calibrate what are called baryon acoustic oscillations, matching those to supernovae and getting a low value for the Hubble constant. But and I agree with that is what you get when you start in the early universe. So what matters is it's like you're building a bridge on two shores, and you start at one shore or the other shore, and you're not matching up, and you got to really keep careful track of which shore somebody started with when they made their Hubble constant measurement. So in that particular paper, DES started out on the early shore. They could have started out on the late shore, and they would have gotten a high Hubble constant, because their measures were basically of what I would call intermediate products. They were measuring, they were building links in the bridge, but they weren't, links that are naturally calibrated to one side or the other until you make that decision.
Dominic Bomans asks, is the slight drift of the tip of the red giant branch H0 mainly due to the calibration problems?
I think there's no doubt that calibration of tip of the red giant branch is, it's just intrinsically more challenging, simply because, you cannot, as I said, you cannot identify a tip of the red giant branch star and observe its parallax with Gaia, and then do that many times like you can do with the Cepheid variables. So you can only measure it to groups, large groups, and those groups have to be big enough that they've populated the red giant branch. And so, that's been more challenging. It's been done in the Large Magellanic Cloud, but unfortunately, the Large Magellanic Cloud is quite dusty. And so there's been debate about what is the amount of dust in front of the tip of the red giant branch in the Large Magellanic Cloud. I'm hoping that Gaia helps sharpen this up as well, but, I think that, we'll just have to wait on more progress.
Alessandro Pizzella asks, what about time delay of multiply lensed supernova images? Can they give important additional constraints?
So, I don't know, the business about multiple lensing for Hubble constant has been challenging recently. I would say a few years ago, people made, some reasonable assumptions. So it turns out you need to know what the mass distribution is in the lens itself, the galaxies or even clusters that are doing the lensing. And people made simple assumptions about those, and they were getting these, high values of the Hubble constant, same thing we're getting, which would be consistent with late universe measures. But, as a lot of scrutiny has come on this, people have realized, those assumptions were actually fairly important to the measurement. So when you relax the assumptions about mass distributions for lensing and make that part of the problem to solve, the constraints become fairly weak. Now, that can be a little bit less of an effect for supernova lensing if there's a cluster involved, but not insignificant. And so I would say that we need to learn more about mass distributions in order to turn lensing into a really sharp tool for measuring the Hubble constant. Until then, I think it's going to have large uncertainties.
Abhishek Yoshi asks, sorry, no, it's good. Thank you for your presentation. As the rate of expansion of the universe increases, what is this effect on the galaxies?
Not very much, fortunately for us. Galaxies have always been more or less immune to the expansion of the universe, and that's because they have strong attractive gravity. They are locally very dense compared to intergalactic space, and so they hold themselves together with a normal attractive gravity and more or less, thumb their nose at the expansion of the universe.
Roberto Trotta says, if thus you recently forcefully pointed out that the H-notch discrepancy really is an intrinsic magnitude discrepancy between local and higher Z supernovae, could supernova 1A evolution be a factor?
Can you read that question again? I missed a few.
Sorry.
keywords.
If stuff you recently forcefully pointed out that the H-notch discrepancy really is an intrinsic magnitude discrepancy between local and higher redshift supernovae, could supernova 1A evolution be a factor?
So I would say what George Eftalthio pointed out, and I think that was very fair, is one needs to be careful when one is taking the Hubble constant measurement that involves the use of low redshift type 1A supernovae, and then in addition takes a supernova data set like compilation like Pantheon, which also involves low and high redshift supernovae. Those things now have some covariance. You can't just combine those without taking account of the covariance. So it was really more about methodology, which I agree with. It wasn't any kind of explanation or resolution. However, having said that, right, one could worry about, some kind of evolution of type 1A supernovae. And that's where we run into really this problem that, we're not talking about very high redshift. When we talk about the Hubble constant measurement, that can be done, only out to a redshift of 0.1, which is, only a few 100 million years, very little look back time. We get a much bigger ability to check evolution just in nearby galaxies that themselves have different ages because they're, early types or late type galaxies. And then that is still in conflict with simply, the cosmic microwave background with LambdaCDM and let's say baryon acoustic oscillations. So that's why I'm saying it takes multiple catastrophic failures. Even, evolution of type 1A supernovae wouldn't do very much to this because you could eliminate the high redshift supernovae from this problem and you still have the same problem.
Hans Zinneger wants to know what you think about alternative gravitational theories like Mond or scale invariant cosmologies. Are those valid challenges to LCDM consistent with the data?
Right. Well, it's always valid to try to alter gravity. But then, as I said, you can't just, do that and test it on the Hubble tension problem. You first have to run the gauntlet of, so many other precision tests of cosmology. And, most of them won't make it, without a lot of fine tuning. That's, there's still vigorous debate there, but, I have not seen any very attractive modified gravity theories that looked promising and then, would be something you'd confront the Hubble tension with. But it is certainly possible. I mean, I wouldn't rule that out. You're just, there's a lot of work to do to demonstrate that could be true.
Okay, we promised to let you go at noon your time, 6 our time. I'd like to thank you very much again. We still have more than 200 participants also listening to questions and answers. It was a wonderful talk. I want to thank the EASY team, in particular, Willi Werfler and Andrea Fischer, also for the support beforehand. And thanks again, Adam, was wonderful, great. Thanks for giving this nice presentation. Thank you.
Sure, thank you.